So in this lecture, I want to go through the catabolism of the nucleosides that we're looking at, particularly looking at the heterocycles. But I mean, I guess we have to include the ribose chain for a lot of this. So we'll just say the catabolism of nucleosides. Okay, and so it's best to sort of just take these one at a time. So let's start with cytidine. So cytidine gets converted actually into uridine. Helpful to know for thinking about the source of these nucleosides as they become nucleotides and ultimately get incorporated into the central dogma more directly. So what we do is we take our heterocycle. So we're looking at the pyrimidine. Now the heterocycle here has the double bond to the carbon nitrogen, replace the double bond oxygen, and there's an NH2 up top. So it's here that I want us to recognize that what we have is an enamine that's embedded within an aromatic ring. So there's opportunities for that enamine to get converted into a carbonyl by way of hydrolysis. And in this case, we would get an amide after we underwent hydrolysis, and that would give rise to uridine. And that's exactly what happens. So what we see here is the enzyme, I believe it's just cytidine deaminase. Is going to convert this enamine into a carbonyl. Let's go ahead and just draw that as the carbonyl. We have an amide. And we have our uridine. Okay, so we start with cytidine, go to uridine using cytidine deaminase. Now in both cases, I've got I'm just going to write sugar here. It could be ribose or deoxyribose, depending on the nature of the nucleoside that we're looking at here. And if we look, what we put in here is water. What we get out is NH3 as we convert that enamine into a carbonyl. So let's look at the mechanism a little bit in more detail. So we'll just discuss some mechanistic detail, and I say some because we have to consider that there's a lot of like hydrogen bonding interactions that are at play that really, change the way the curly arrows actually should look. Like, for example, we have some sort within the enzyme active site, we probably have some hydrogen bonding interaction to activate this position so that a water molecule could come in and attack, but that water molecule is hydrogen bonded to some sort of basic residue within the active site. And so what happens is that adds there to there, and we probably, we could use either the lone pair or the sigma bond to provide the source of electrons for nucleophile addition. Because at the end of the day, that hydrogen falls off of the O, giving us just an OH, and the other hydrogen gets added on to the N. Then what we can do is we can hydrogen bond to some sort of acidic hydrogen and then have some base come in and hydrogen bond and tug off this hydrogen. So we go here to here. So again, with the curly arrows, it's just not as straightforward as the typical organic reaction in a flask with like organic solvent and isolated species. So sometimes you have to rely on the formation of these hydrogen bonded complexes, which means hydrogens can be readily added and removed. And the net outcome here is that the two hydrogens on water get sort of transferred over to the two nitrogen atoms that are involved, one that's becomes an NH of an amide, and the other one that gets lost is NH3 in ammonia. And so, sorry, that's a little bit more sloppy of a drawing, but that's uridine, that's cytidine. Okay, so cytidine goes to uridine. What happens to uridine? Whoops, sorry, don't mean to hammer through that too quickly. So let's look at the catabolism of uracil, which is ultimately going to provide us with some insight into the breakdown of the nucleoside uridine. So uridine is the nucleoside, and then the basic component of uridine is uracil. And if you haven't caught it so far, or haven't seen this before, the names for the various nucleosides, the cytidine, uridine, adenosine, thymine, are all thymidine, excuse me, are all, and then guanosine are all kind of derived from the base, the name of the base that's used. Okay, so what I'm going to do with uridine now is draw out the actual ribose core, and let's leave it as ribose, the RNA version. So we have two OHs down, and the other two structures are up. So over here we've got, just remember that uracil has the two carbonyls, kind of alternating carbonyl, nitrogen, and then the rest of the pyrimidine core. And let's go OH here because this is the nucleoside and not the nucleotide. Okay, so the first enzyme that we're going to use is one that's common to all of these, and that's the phosphorylase enzyme, nucleoside phosphorylase. So first of all, PI is inorganic phosphate. And this uses, I'm going to label this kind of like the book does, enzyme 1. And so we've actually seen this before in a paper. They were going in the opposite way to assemble a nucleoside, but a nucleoside phosphorylase uses inorganic phosphate to cleave the CN bond, where C is our anomeric carbon. And I believe the outcome is a ribose 1 phosphate, or deoxyribose 1 phosphate. Okay, so what does that actually look like now? Let's get some structures on the screen while you're capturing those words. I'm going to consider my entire ribose structure, except now the base is gone. So OH down, OH down. Now it turns out that in this case we replace the N at the anomeric position. And maybe I'll highlight that anomeric position for you. So there's the anomeric carbon. That's the carbon that is a hemiacetal, or a full-blown acetal, or an NO acetal in the case of the starting material. But now, instead of having an N, we have a phosphate. So we use phosphate to do an ACE, or a lysis, or a breakdown, to release the base and make some ribose 1 phosphate. So now we have full-blown uracil. It's not uridine anymore, it's that base uracil. Okay, so that's the first step in the catabolism of uridine, is to do a phosphorylase to break down the sugar and base to the separate entities, sugar and base. Now the opposite could occur. We've seen that before. So this can work in reverse. To synthesize nucleosides. Okay, So what I want to do now is consider what happens to the uracil. So the uracil gets taken up, and the first thing that happens to it is that its double bonds are converted into, its carbon-carbon double bond is saturated. So we need to do a reduction step where we convert this carbon-carbon double bond in the starting base into a carbon-carbon single bond. So that's going to be the addition of two hydrogen atoms at this position using NADPH. So this is a lot like NADH, but it's got a phosphate, so that's what the P is for. And then what we get at the end is a lot like NAD+, but it's got a phosphate. So the phosphate's usually just there for molecular recognition. It works with certain enzymes. So you could think about that as an NADH to NAD+ strategy. We're just adding nucleophilic hydrogen, doing in effect just reducing double bonds, which we've done before. This enzyme is called just a Dihydropyrimidine Dehydrogenase. So this is the enzyme. Dihydropyrimidine Dehydrogenase. Okay, so that's a mouthful for sure. I'm just going to make a new page here. I'm going to bring this down while I press this button a bunch. Okay, so the name here is certainly a mouthful, this dihydropyridine dehydrogenase. What I want to point out is that the name dehydrogenase kind of suggests this is an oxidizing enzyme where we're removing two hydrogens, but we're adding two hydrogens. And that's because enzymes are sometimes named for their reverse reaction, depending on the context from which they were discovered. So here we're actually using this in the opposite direction of which the enzyme was named, which is why, because we're adding two hydrogens. So that explains the second word here, the dehydrogenase. And that's a critical word, right? We're adding H2 or removing H2 from a system. Now, why is it dihydropyrimidine? That's a big word. Well, we've seen pyrimidine before. That's the parent heterocycle to these nucleosides, the six-membered ring with two nitrogens alternating. Uracil is a pyrimidine. And so this is that's where the pyrimidine part comes from. But why dihydro? Well, remember, this is named for the opposite case where we're working backwards. We have a pyrimidine on the left, or an oxidized version of it anyway. We have pyrimidine on the left, and to get there, we start with a dihydropyrimidine. Let me say that a different way. We have a pyrimidine on the left. If we add two hydrogens to it, we have a dihydropyrimidine. So I show those two hydrogens drawn explicitly. So the enzyme's named dihydropyrimidine dehydrogenase because it takes that starting material and typically makes it from the product of this reaction. Okay, anyway, I feel like I talked too much there. We can go through that mechanism ever so briefly for this enzyme. What's happening here is this enzyme uses FMNH2 as a cofactor. Now, FMNH2 as a cofactor is a Flavin or Flavin cofactor that provides or removes H2, depending on where you're at. So a Flavin cofactor, it's Flavin mononucleotide, and then either H2 or without the H2. Okay, so let's draw FMN first. So FMN is going to be two six-membered rings where the middle ring has nitrogens, and then the right ring is actually derived from a pyrimidine. We can tell by the arrangement of the two nitrogen atoms. The carbonyls actually looks a bit like uracil. Now everything is aromatic. Just two methyl groups over here. Everything is aromatic by allowing the double bonds to alternate this way. Now, if we add H plus and H minus to this, we get the same 6-membered ring system attached to a 6-membered ring system. Now I'm not going to add as many double bonds to the right 2 rings yet. This should be an H, by the way. Okay, we put the double bond here, then we're going to have an H here and here. Now, this structure, the nitrogen is actually attached to what looks like a ribose. And so, anyway, we don't have to worry about that. That's what that squiggly line is for. But this is then FMNH2. And so we've seen these Flavin oxidizing agents before. So what we can do is we can pull off 2 hydrogens or add 2 hydrogens by way of an H minus H plus pair. Okay, so what this does is this can, this will go this way, and then uracil will go this way to form dihydrouracil. Just drawing these structures over and over again to get good at them, right? Okay. Now we're at dihydrouracil. What's going to happen here? Well, it's a series of, it's a couple of hydrolyses happen at this point. So dihydrouracil will be hydrolyzed. Now, if you look at this, this is kind of an interesting array of atoms. And so we can actually poise ourselves to add water to this. Now, if we add water, let's say we add water to the oxygen, and that's mediated by base. If we add water there, we can get somewhere, but the product that we get actually doesn't sort of suggest that's where we're going to add. Instead, we're going to add to this single amide as opposed to the carbamate. Sorry, that's probably not the best note-taking strategy. So if we add here, so we're going to add, come up, we'll go ahead and just draw that tetrahedral intermediate. If it were biochemistry, we wouldn't, but, and I'm going to go ahead and just allow hydrogen transfer to occur because the water is getting deprotonated, as this is probably hydrogen bonding to something in the active site. Okay, now we have base, come down, or deprotonate here to allow this to come down, and this is probably going to simultaneously, I'm going to draw that curly arrow coming from the bond. This is probably simultaneously hydrogen bonding to a good H plus donor. And so water, in effect, converts the top carbonyl into a carboxylic acid, which then releases this interesting carbamate. It's more like a urea structure, I guess. Now, if we add water here and do another hydrolysis, what we will do is lose a few ways you could lose this. I'm not too concerned about it, but what you do is you, let me think, which of these probably wants to be lost? I see, it's hard, I mean, it's all governed by the enzyme active site, but let's go ahead and just draw this where we replace the right NH2, the right nitrogen, with OH. That's going to release ammonia. Okay, now this core piece right here is unstable because it's prone to decarboxylation, where if I draw a curly arrow, sorry, I'm going to have to draw this hydrogen with a bond, we would have some base come in, come here, and then we would go to some other acid. I'm sorry I'm doing it this way. It's just probably how it's happening. Hydrogen bonding donor allows the substrate to orient itself in the active site, and then some basic residue kind of reaches out, deprotonates, and triggers this whole chain of events to happen. Okay. Anyway, what you get then is NH2 plus, and I guess I already showed the loss of CH2, but CO2, excuse me, but the NH2 is now on a chain that's on a carboxylic acid. Now, what you'll notice about this is this sort of looks like an amino acid, except the amine is at the beta position. And so this is actually beta alanine, because we've taken alanine with its methyl group at the beta position. We put the NH2 out there as opposed to the alpha position. Okay, what you can do at this stage is an amine swap. We'll talk about this when we get to the peptide chemistry, where you can convert an NH2 into a carbonyl. So we get a an aldehyde. So this is now, looks like malonic acid, but it's an aldehyde. So this is malonic semi-aldehyde. I think this is a cool molecule. Now, the book doesn't go into much detail as to what happens next. So we have to do some sort of oxidation event. We have to make a thioester. There's a few ways we could think about doing it. They seem to suggest we don't actually go through malonic acid. So it makes me think we have this sort of TPP thiamine diphosphate interaction, but they don't say that. So I could just be wrong. But anyway, we will oxidize and then make a thioester. And the thioester will ultimately be with CoAsh, or we're going to make a CoA thioester. What we ultimately get is what's called a malonic acid half thioester. So malonic acid is 3 carbons. Better focus here. Is 3 carbons. With carboxylic acids on the 2 outsides. So, oh my, such good apple pie, all that stuff for our fundamental dicarboxylic acids. The M for my, that's malonic acid. And so this is malonyl CoA, or it's a malonic acid. Half of it, though, is a thioester, malonic acid, half thioester. And these molecules have very interesting properties. Now, this will intercept numerous metabolic pathways within the system. So that's uracil. Uracil ultimately ends up as malonyl CoA. Now, what we could do is we could look at a similar pathway for thymidine. So if you remember, sometimes it's U, sometimes, most of the time, though, it's T. I guess I should have specified the sugar before. The sugar was indeed ribose if we're using uracil, right? Well, maybe that's for the coding. Anyway, if we're with this structure, now we're in deoxyribose because we have uracil, goodness, uracil, 2 nitrogens, goodness. We have uracil, but with a methyl group, so that's thymidine. Uracil with a methyl group is just thymidine. We need that methyl group there to make, do our DNA stuff. Okay. We're going to, first of all, as we catabolize this species, we'll go through a very similar route. I'm not going to show all the steps. But the first step is the phosphorylase to, just like we did with uridine, converting uridine to uracil, we need to clip the thymine base off of the sugar. In this case, the sugar is definitely deoxyribose because we're working with T, which is part of DNA. All right, so hopefully you're starting to get comfortable with that uracil-like structure. We're just putting a methyl group at what looks to be the 4 position of the molecule. Okay, now at this point, we're going to go through the same steps. We're going to go with H2 addition by way of FMNH2. And that will reduce the double bond. So we're going to do that. Then we're going to add water. Then we're going to add water with loss of CO2, and then we are going to oxidize and thioester rise. And what we ultimately get is a very similar molecule, a malonic acid half thioester, where the thioester is a CoA thioester, except now we have a CH3 present. And you could work through that pathway if you'd like. That CH3 corresponds to the CH3 that came with thymidine. Now that's going to proceed through a different set of metabolic pathways, but the steps to get from the base, or really even the nucleoside, the deoxyribose nucleoside, onto the malonyl CoA are the exact same. Okay, probably with subtly different enzymes and that sort of thing. Okay, so those are our pyrimidines, right? We went through thymidine, we went through uridine, and we started though with cytidine to get there. So those are our pyrimidines. Next, we'll move into the catabolism of purines. These are these slightly more complicated heterocycles because we have an imidazole attached to the pyrimidine. So here is our ribose sugar attached to imidazole, and now we're going to attach this to our pyrimidine. So we have to be aromatic at both rings. Now if we stick an NH2 up here, we're at our favorite nucleoside. Sorry for the brainwashing here, but adenosine is just so interesting. So here we have adenosine. So let's start here with the catabolism of adenosine. So the first thing we're going to do is have an enzymatic process that converts H2O into a good nucleophile so that it can swap, I've got two greens too close to each other, it can swap this NH2 with the H2O. It's going to make ammonia as a result. And the outcome of this is going to be a purine now with a carbonyl at this position. So we've swapped the NH2 for an oxygen, then we underwent tautomerization. Okay, now we're still connected down here to our sugar. Now this molecule is called inosine. And so this is kind of like the cytidine pathway where we first do a hydrolysis reaction before we clip things off with the phosphorylase. But now we're going to do the nucleoside phosphorylase reaction. We take inorganic phosphate and we get to the sugar phosphate. So the sugar 1-phosphate, sorry for the sloppy handwriting there. The thing I want you to focus on though is converting inosine, which is a nucleoside, into this structure where now we have an H on the imidazole. Okay. So this structure is called hypoxanthine. I don't have a good sense of how we can remember that name, so I'll just keep moving on. Next, we're going to do a series of oxidations. And ultimately, what we're doing is having H2O and water engage these species to form hydrogen peroxide as a byproduct, but we're going to substitute the hydrogens here and here with oxygens, which will tautomerize to carbonyls. And so the first one of which is going to go to the south east, leaving the imidazole intact. And so we do an oxidation there. One thing you can think about doing is squeezing an O in that carbon-hydrogen bond and then doing a tautomerization to an amide. This structure is called xanthine. So we went from hypoxanthine to xanthine after an oxidation process. And we're going to finish this off with another oxidation process. Now I couldn't tell from the reading, but I believe these oxidation processes aren't necessarily mediated by the same reaction. One thing that's interesting about this is that you form H2O2 as a byproduct of this reaction, hydrogen peroxide, which you can imagine if you're a cell, you're probably not too happy with. But it turns out there's an enzyme called Catalase, which is super effective at just taking hydrogen peroxide and converting it into water. And then I believe you have to have oxygen as the byproduct. Not for sure, though. I just know that hydrogen peroxide reacts very quickly with catalase. Like it's a super efficient reaction. It's not a big deal. All right, so in this structure, we're going to have a double bond cutting straight through the middle. And this structure is finally called uric acid. So if we backtrack a little bit and look at what we've done with ribose, we're with the adenosine, which we had adenine attached to ribose. We first hydrolyzed the adenine base to form the inosine nucleoside by just converting the NH2 into a carbonyl. We then did the phosphorylase to release the base. That was then just hypoxanthine, but that's not a huge change to us in terms of the structure of the base in the heterocycle. But then we do a series of oxidations using oxygen as our oxidizing agent to add carbonyls at two positions to make convert hypoxanthine into xanthine and then ultimately into uric acid. And uric acid is readily excreted in urine. It turns out that if you there's some metabolic pathway where if you are starving, you'll start noticing that this will actually be excreted in higher doses in the urine. You can actually see it crystallize out after the urine dries. So if something happened, one of my children was born, they were inadvertently not fed the proper amount. It wasn't my fault. Anyway, they said 15 mils, but it was supposed to be 50 mils of formula. And poor kid had uric acid crystals in his diaper. We got him fed. He finally pooped. We got to go home from the hospital. Anyway, interesting stuff. Okay, so uric acid readily excreted in the urine. So now we've taken adenosine, hydrolyzed it in inosine, and then taken it through a series of oxidations to make it something that can be readily removed by the body. What I want to do is look at one of the first oxidation step. So let's, more detail, I guess, would be the name of this little section. More detail on the oxidation of hypoxanthine. So this was the first oxidation that converted the first sort of carbon-oxygen double bond into a carbonyl. So this happened at the pyrimidine-like ring. All right, so what's happening here? Well, we have a very unusual cofactor for this enzyme. It's a metal molybdenum reagent. Okay, so I'm going to draw this H out specifically, but we're going to have a molybdenum reagent, which is got some ligands here. Gadzooks, you know, this is in the book, but is this something where we want to count electrons? Well, we all know the answer is yes to that question. So let's do this mechanism. We're going to count some electrons on this. But this then goes to the rest of the molecule here is a Pyranotaryn, I believe is how that's spelled. Pyranotaryn cofactor. So there's a small molecule cofactor that adducts to an unusual metal center. Now this is a molybdenum in the +6 oxidation state. Now, do we see that +6 oxidation state? Yeah, sulfur with +2, or excuse me, sulfur is a divalent ligands, so that's providing -2. Oxygen double bonds a divalent ligand, providing -2. And by sulfur, I meant the sulfur molybdenum double bond was a divalent ligand. Then we have 2 sulfur mono valent ligands, and then an oxygen monovalent ligand. So we're missing one of our ligands. The book says this is a molybdenum 6. So it'd be interesting to know what the electron count is, but overall this complex must then be positively charged, right? Yes, and I'm sure that's just countered by some phosphate. That's kind of the trouble with these, with counting electrons. Do I have this right? 2 on oxygen, 4 on sulfur, 5, 6. Ooh, 7 puts us at -1, but the book says it's a 6 oxidation state. So it makes me wonder what the nature is of that water and how some of these ligands are behaving. Very interesting. Okay, but we know this is the +6 oxidation state. Okay, from the book. So what we have here is a basic residue in the active site is going to grab this H, which is then going to fire these electrons into this carbon-nitrogen double bond by way of like a nucleophilic water addition. We're going to go up to the nitrogen, then we're going to swing back down, and we're going to push this hydrogen off in an interesting reduction event so that it hits onto the sulfur molybdenum double bond. That's going to have to push electrons into the molybdenum center. Now at this point, our base that is to be oxidized is now covalently bonded to the molybdenum metal center, because now we have this oxygen bond right here, which is attached to molybdenum, which is then on sulfur with an H here, double bond of 5-membered ring, rest of our molecule. Okay. So at this point, what happens is that water actually comes in. So we needed that sulfur atom to facilitate sort of the removal of the CH bond. But now water is going to come in and replace all of this. You could have it attack, you could attack either the carbon-nitrogen bond or the molybdenum, in which case you'd crack this bond, or if you attack the carbon, you'd crack this bond. Either way, what we get is a structure now where we have an OH. Now I'm kind of worried I went fast through some of the tautomerizations before, so I'll show the enol structure here. And while this is aromatic, we actually see a better tautomeric, a more stable tautomeric form at equilibrium, where we have the actual amide being present. Okay, so now this would be keto form, and we get there by tautomerization. Keto. Okay, so there's the oxidation. Now what we get, if we want to just take a second and look at guanosine super quick. Guanosine's pretty easy now that we've seen all these steps. We can actually intercept the adenosine pathway with guanosine. So guanosine is going to be another purine. Now here's the thing about guanosine. We've already got one of the carbonyls we need to get to the xanthine intermediate. So this will ultimately go to xanthine. That would be a nice header to these notes, wouldn't it? As opposed to like a random arrow. But let's label this guanosine. Let's leave some space up here. Guanosine catabolism. This goes to xanthine, which then ultimately goes through the usual procedure to get to uric acid. Okay, so here's guanosine. Now, what I want us to notice about guanosine is that if we compare that to, oh, I've got the structure right here. So this is now xanthine, right? Because that mechanism I showed you up above was the oxidation of hypoxanthine to xanthine. Okay, so xanthine, let's just look at the structure of xanthine up and to the right. If you look at it, okay, yeah, we're still attached to our sugar. Guanosine is, we're still attached to the sugar, but otherwise we've already got the carbonyl at the top. We've already got that carbonyl. So that happened in the first hydrolysis step where we converted the NH2 enamine to a carbonyl. Okay, so that happened at the first step. Now, the other step we had to do to get from adenosine to xanthine was this CH oxidation to convert a CH bond into a carbonyl. If you look down here, we have an enamine that can be hydrolyzed in much the same way as the first step of the adenosine catabolism pathway to give rise to a carbonyl. So we can actually just do a single hydrolysis reaction, and we have to cleave the sugar away using a phosphorylase. But after we remove the base from the sugar, it's a single hydrolysis reaction as opposed to a really funky CH oxidation, and we're at xanthine. And then from xanthine, we can do the other oxidation using that enzymatic machinery to get us to where we need to go. So that's sort of the breakdown. The goal is to get to xanthine. So the first step is the phosphorylase with inorganic phosphate to give ribose 1-phosphate. And more importantly, for the purposes of this lecture, we're going to get the purine base now released from the nucleoside. So this is now not guanine, but not guanosine, but guanine. Okay. Now what we're going to do is a hydrolysis reaction. I'm going to redraw the base down here. If you have room in your notes, you should be fine. I just ran out of space to effectively portray this. But we're going to see another sort of array where the guanine comes in. You can have it probably hydrogen bonding here. Well, let's just start simple. Okay. The OH is interacting with some base, which is going to go here, and promote addition here. So we can go down and back. That's probably supported by, well, yeah, it's definitely supported by hydrogen bonding interaction to an enzyme. That's going to allow us to get to this NO-acetal, just an acetal where one of the oxygens is a nitrogen. Sometimes people call these aminals, that's fine. But let's draw the structure because molecule structures are better than words. Okay, so we go here, and then A minus, that just lost its hydrogen previously, is probably going to attack here and push electrons over here. That's one way to do it, or let's keep it simple. Let's have hydrogen bonding. Sorry. Lone pair is going to add to an acidic hydrogen at the same time that a base is going to grab the OH, push the electrons down to make a carbon-oxygen double bond. We'll just stick with that as opposed to having an enolization step. I keep forgetting this H over here. Now that the ribose is lost, we have the free base. Whew. All right, and there's xanthine. Yes, xanthine, which can be oxidized to uric acid in a single oxidation step using that other enzymatic machinery, and we're done. We've got the purines taken care of. We did adenosine all the way to uric acid. We did guanosine and intercepted that route using xanthine. If we go back and think about the other ones, how did we start? We started with cytidine. We did a hydrolysis reduction, blah, blah, blah. It got to an aldehyde, which we oxidized to a malonic acid, half thioester. And actually, cytidine went to uridine. Uridine went to uracil. Uracil went to all of that stuff. And then we took thiamine, did the exact same thing to get a methylated variant. So we've done all of the nucleosides and nucleotides have been broken down into something that can be readily excreted or something that will be intercepted and then used into a subsequent pathway. Okay, so that's catabolism. We'll next look at building these things up, the biosynthesis of the various nucleotides. Okay, well, that's it for this one. So we'll see you next time.